All right, gentlemen, playtime is over. It's time for you to learn Bayes' theorem. Now, you already know a little bit about probability. So, let me ask you, suppose I have two cups, cup A and cup B, but I don't tell you which one is which. If you pick one of these cups at random, what's the probability that you chose cup A?
1/2.
1/2, because there are two possible outcomes and one desired outcome, and that's how you determine that sort of probability. You say one desired outcome over two possible outcomes, giving you a probability of 1/2. You would expect it to happen 1 out of every 2 times. Now, some people think in terms of percentages. Notice that 1/2 is just 50%, so that's what you would say the probability of picking 1 out of 2 things is. Normally, when we're dealing with probability, we speak in terms between 0 and 1. 0 would be something that's impossible. So the probability of me having a square circle is 0. It's impossible. A 1 would actually be 1 over 1, or 100%. That would mean something that's absolutely certain. So if I say tomorrow it will either rain or it won't rain. Well, no matter how things turn out tomorrow, it's either going to rain or not rain, so that statement is going to be true every single time. So if you want to say something that has really no content, it's something that has no content to it, you can say tomorrow it will rain or not rain. Now what we're going to do is examine Bayes' theorem, but we're going to do some diagrams because this will make it much easier to understand. So think of a shape. It doesn't have to be a shape like this, but let's say we have a shape here and that this represents all possibilities. All possibilities are represented within this shape. So this has a total probability of 1. If I wanted to say that I have 2 possibilities and they're equally probable, how would I divide up this space to show that in a diagram form?
Cut it in half.
You cut it in half. You can do this however you want. You can cut it this way, you can cut it this way. You could even draw a shape in the middle as long as it's taking up half the space. But we'll keep it simple, draw it like this, and we'll say here's A and here is B. And this would be different if you had more possibilities. So, Blaze, if I flip a coin twice, how many possibilities are there?
If you flip a coin twice, there's tails, tails.
Hang on. Let me draw them up here. Just first, how many possibilities are there?
4.
There would be 4. So it would be what? You say tails, tails? Then what?
Heads, tails.
Heads, tails.
Tails, heads.
Tails, heads.
Heads, heads.
And heads, heads. So if you wanted to draw that in using space, since they're all equally probable, you divide it up evenly. You don't have to do it like this. You could divide it up into equal rectangles. But we're dealing with only 2 possibilities because there are only 2 cups. Cup A and cup B. So we have cup A and we have cup B. Now, what I'm going to tell you is that in cup A are 20 red gumballs. We have 20 red gumballs in cup A. There's nothing else. There are no other gumballs. So how you would represent that is all of the space of A is filled in by red gumballs because that's all you can possibly draw from it. In cup B, we have 10 red gumballs and 10 white gumballs. So how would I represent that over here?
Color half.
We color half, right? So you color it sort of like this. And so what we have here are this shaded area represents the red gumballs, and this unshaded area represents the white gumballs. Now what I'm going to let you do is draw, without looking, reach in there and grab a gumball. And you drew a red gumball. Which cup did you draw from?
Most likely it would be A, because there are more reds than B.
But it could still be B, right?
Yeah, it can.
It can still be B.
It's possible.
But you would say probably A.
Yeah.
And what your brain just did there, automatically, was use Bayes' theorem. In a primitive, undeveloped form, you use Bayes' theorem. Your brain understands that certain evidence, go ahead, you can eat it. Your brain understands that certain evidence fits in better with one hypothesis than the other. And so it increases your confidence in one hypothesis where the hypothesis is I drew from cup A, and it lowers your confidence in another hypothesis, namely cup B. So you started off with 1/2 for each of these, but drawing a red gumball increased your confidence here, lowered your confidence that you chose from cup B. Now, notice what happened. When you drew a red gumball, what happened is that this possibility, which that was one possible way things might turn out, it didn't turn out that way. Now, look at the amount of area you have here. This is now twice as probable as this. So, if we talk about the probability of that you chose cup B, what's the probability that you chose cup B?
1/3.
1/3, and that's good because look at what you've done. There are sort of 3 equal areas left over, and this is one of them. So it's 1 out of the 3 remaining areas, and so you'd say you have a probability of 1/3. So what's the probability that you selected your gumball from
2/3.
A? 2/3, right? So now you have a probability of 2/3 for A, probability of 1/3 for B. So the effect of learning that you chose a red gumball randomly from one of the cups was to increase your confidence in A from a probability of 1/2 to a probability of 2/3, and to decrease your confidence in hypothesis B from 1/2 to 1/3, right? So notice, by actually picturing it here, you just sort of knew, you had a sense when you picked one that it's more probable that you chose from one or the other. This can give you an exact number, right? So the probability now, without looking, is 2/3 and 1/3. Good so far?
Yeah.
Now, believe it or not, you just did Bayes' theorem, but we did it in picture form. We did it not in number form. We would say we did it geometrically, not algebraically. So if you put this into actual numbers, you've got Bayes' theorem. So what Bayes' theorem is going to say, with this as an example, is that the probability of, and we can use either one, but we'll go with B, the hypothesis that we selected our gumball from, B. The hypothesis that B is true, the probability of B being true, given that you selected a red gumball, if you want to figure out what that is, that's going to be equal to the probability of B times the probability of getting a red gumball if you chose from B, divided by the probability of getting a red gumball. People look at that and they say, oh, that's very confusing. Well, think about it. This stands for a number, this stands for a number, this stands for a number. You're multiplying this times this and dividing by this. That's elementary school math, so this is not very difficult mathematically. The only tricky part is understanding what these things represent, and once you've got that, you've got Bayes' theorem, because the math is very easy. So once you understand what these are, we're good to go. So all we have to do is figure out what these mean. The probability of B, without the R, is just the probability that you started with. What was the probability before you chose a gumball? What was the probability that you had chosen, that you would choose from B?
1/2.
1/2, right? So you started off with a probability of 1/2. So let's write it again. Probability of B given R is going to equal 1/2. That's one of our values, so the probability we started with, times the probability of getting a red marble, assuming that you drew from B. So going back to this, we started something like this. Assuming you drew from B, what's the probability of getting a red marble? I mean, a red gumball? Half, right? Half of the gumballs are red. right? So the probability of getting a red gumball, if you selected from B, is going to be 1/2. So just 1/2 the space here. 1/2. And your other value is the probability of getting a red gumball regardless. So you have 2 cups. The probability of getting a red gumball regardless of what cup you draw from is, well, you can actually see it visually here, and then we'll calculate it. But look at what you have here. These are all red gumballs, these are all red gumballs, these are all red gumballs, and these are the white gumballs. So what's the probability of getting a red gumball, given that these are all the possibilities here?
3/4.
3/4. 1, 2, 3 out of 1, 2, 3, 4, right? And the other way to do this would be, how many gumballs are there total?
40.
40. You have 20 in one cup, 20 in the other cup. So you have 40 total. How many red gumballs do you have?
30.
So it's 30 over 40. What would that be like?
It would be 3/4.
3/4. So you just cross those out. And then you have 3 over 4. Now, we'll talk about why these different values are important here in a moment. Luke, come in and do this math real quick.
Sure. 1/2 times 1/2 equals 1/4. And then you move the 3/4 up here, and since we are dividing fractions, you flip the second fraction, so that's thirds, and then use them to and that equals 1/3.
Yes, because you're going to cancel the 4s, right?
Yep.
Okay, so you ended up with 1/3. Notice exactly what we ended up with over here, right? Once we drew one, we knew that we hadn't drawn a white one. That left it with these sort of 3 areas. Here, you did it with numbers. And so what Bayes' theorem is doing is it's telling you how to calculate the probability, how to update your probability, how to update your confidence in a hypothesis given some new evidence that has come in. And what Bayes' theorem says is this is going to have 3 factors, right? There's going to be 3 things involved here. One is the probability before you got the new evidence, right? Because you might have, B could have, in a different situation, if you had 1,000,000 cups, right? If you had 1,000,000 cups, then B would have had a probability of 1/1,000,000th, right? And choosing a red gumball might not have helped you become much less confident that you had selected from B. So it really matters a lot how confident you were in the hypothesis at the beginning. But it also matters how probable the evidence is given that hypothesis. Think about it. If there were no red gumballs in B, then you would know that you didn't choose B if you picked a red gumball. If there were all red gumballs in B, that would matter too. Here you have half of the gumballs in B are red, so that's going to affect, we call it your posterior probability, but it's the probability that you have after you've factored in everything you know. So those certainly matter, but notice those aren't the only things that matter, because think about it. You chose a red gumball, and it lowered your confidence in B from 1/2 to 1/3. Why? Because getting a red gumball was more probable over here on A. So it also matters how probable the evidence is on other hypotheses. If there were no red gumballs over here in your A cup, then what would, if you picked a red gumball, what would be the probability that you chose from B?
1.
1, right? You would know. So think about that. These numbers aren't changing, right? These numbers, your numbers for B aren't changing. You're starting off with 1/2, and you have half of your gumballs are red. And yet, A is a huge factor in how confident you are afterwards. If A is completely red gumballs, there's nothing but red gumballs, then getting the red gumball actually lowers your confidence in B. If there were no red gumballs over in A, then getting a red gumball would increase the probability of B to 1. And let's say that half of the gumballs in A were red. What would how would drawing a red gumball change your confidence?
It wouldn't.
It wouldn't change it at all, right? It wouldn't tell you anything. So, and you can see why this is important. So suppose that there were no red gumballs over in A. Well, watch what happens. These are still the same, right? You start off with probability of 1/2, and it's still half of the gumballs in B that are red. So these numbers don't change. What changes is this number. The total number of red gumballs would now be 1/4, right? Taking it, there's only 1/4. There's 10 out of 40. So this number would switch to 1/4. And so now it's going to be 1/2 times 1/2, which is 1/4 over 1/4. What's 1/4 over 1/4?
4th over 4.
4 over 4. So that's going to just be 1. So notice you can see here in picture form what's going to happen with the numbers over here. So that's why you need all three of these numbers. And so once you understand what those three things are, then you can write Bayes' theorem in a more general form, which people look at and they get intimidated, but as long as you keep an actual example in mind, it becomes much less difficult. But a general form of Bayes' theorem will be the probability of some hypothesis given some evidence that you have come upon is going to equal the probability that you started with times the probability of that evidence given the hypothesis divided by the probability of the evidence. And so all this is saying, again, you start off with a certain probability, you get some evidence in, and the evidence has a certain probability on that hypothesis, and that evidence had a certain probability regardless of where it came from. So that's all Bayes' theorem is saying. Not very complicated. Again, this times this divided by this. Actually applying Bayes' theorem can be much more difficult in practice because lots of times you're not just dealing with two hypotheses. You might be dealing with 10 or 20 or 30 or 40 hypotheses, and you have to keep in mind there are hypotheses you haven't even considered. So when people are discussing Newtonian mechanics, they haven't even thought of Einstein's theory of relativity. It wasn't even in their minds. So in figuring out, hey, this is how probable the evidence is, that can be very difficult to do when you're not even sure what all the hypotheses are. And the other problem is, if you're talking about using this for science or history, you usually don't have specific numbers. If I say, what's the probability of gravitational time dilation? Well, it's not something I can put a number on the way I can if I'm counting gumballs in a cup. So things can actually get difficult in applying it. But as far as what the theorem is actually saying, this is straightforward and non-controversial. So, you understand?
Yeah.
One more question. We've seen that Bayes' theorem is actually pretty easy. Is it easy to rock a rhyme that's right on time?
Yes.
It's tricky.
It's tricky to rock a rhyme, correct. All right, now that you know that, it's easy to use Bayes' theorem. It's tricky to rock a rhyme. Get out of here. Go. I've taught you everything I can possibly teach you.